You might have heard of the term image processing and must be thinking what exactly it is and how can I actually implement it with using any programming language. Well, we brought to you this course on image processing with Python so that you can understand all of the concepts of image processing. So image processing is basically a subdomain of computer vision, and computer vision again is a subdomain of deep learning. So in this course, we'll properly learn everything about computer vision and image processing and also learn how to implement it using Python.
Before we get started, I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.
So we'll look at the agenda first. So we'll start off by doing some image processing fundamentals using this library in Python called as Willow. And then we'll have a comprehensive introduction to computer vision. Now, to implement computer vision, we have special type of neural networks called as convolutional neural networks. And we'll understand everything about CNNs. And then we'll have a comprehensive intro or comprehensive deep dive into CNN architecture. So we'll start off this by understanding the concept of image processing. Now, I believe most of you would have Facebook accounts. So whenever you log on to Facebook and let's say you upload a picture. Now over there, let's say you have a group picture where all of your friends are present, and if you take your mouse and hover it on someone's face, you will get the name of that person. So here what you're doing is you're tagging the person's name to that person's face. So what is happening over here? This over here, friends, is an example of image processing. And this is a very good example of computer vision. Now let's actually understand what is happening in the background. Let's start off with black and white images or grayscale images. Now whenever we talk about grayscale images, the range of a grayscale image would be between 0 and 255. Now, as a human being, you're able to see this car. So you know that this is a car and this is how a car looks like. But if you take a machine and feed an image of this car to that machine, it will not understand that this is a car. What the machine will actually see is, it will see it as a matrix of numbers. And since this is a black and white image, you will have a matrix, and inside this matrix, you will basically have numbers in the range of 0 to 255. And this matrix is basically the size of your image. Now, when we say a 36 cross 36 image or 128 cross 126 image or whatever the size of the image is, this is what we basically mean. So here we basically have a 2 cross 2 image. And each cell over here represents your pixel. Now you would have heard of this term called as pixel, isn't it? So that is basically your each cell value. And each cell value, if it is a black and white image or if it is a grayscale image, you will have a value between 0 and 255. So here, what happens is, this is a 2 cross 2 image, which would basically mean the length is 2 and also the width is 2. And here, the values. So here it has to be between 0 and 255. Similarly, this value has to be between 0 and 255. And that is how we are filling this up. And the machine sees this image of a car like a matrix. And when we talk about Python, we have this library called as NumPy. And with the help of NumPy, we can create all of these matrices. And inside those matrices, we will store these images. So this is a black and white image or a grayscale image. Now let's talk about a colorful image. We've got something called as an RGB image. So in this RGB, R stands for red, G stands for green, and B stands for blue. And over here we'll have three matrices for each of these three color channels. So we'll have one matrix for the red channel, another matrix for the green channel, and another matrix for the blue channel. So this image which you see is basically being represented through these three channels. And each matrix over here has certain values, and again for red channel again you will have values from 0 to 255. Similarly for green the values will be between 0 to 255, and same for blue as well. So this is how we store the images in a computer, and this is what a machine basically reads. Now let's go to Python and let's do some image processing with Python. So I've opened up Jupyter Notebook over here. Now to do basic image processing, I have a library called as Pillow. So if you haven't yet installed it, you just need to go to your Anaconda prompt and write down install Pillow. Now once you install it, you'd have to load it. So here I'll write down from PIL import. So I would have this called as image. So let me actually make this as capital I. So from PIL import image. So I basically want to load an image object. So here I'll write down image dot. I have this method called as open, and over here I've just uploaded my photo. So I've named the photo as Bharani. I have something called as bharani.jpg, and I am opening this. Now let me just hit on run and let's see what do we get. So here you guys see we've got my really beautiful face over here. Now what I want to do is I want to store this object into this new variable or new object called as Bharani. And now what I want to do is I want to show it properly to you guys. So I'll have bharani.show. I'll hit on run. Now let me open this up, and as you see what I've basically done over here is I had loaded up this photo onto my Jupyter Notebook, and using the PIL library I've been able to open this up. Now let me do some basic changes over here. Let's say if I want to rotate this, then I'll write down Bharani dot, let me write down rotate, and let's say if I want to rotate this by 90 degrees. So I'll just write down rotate 90, and here you see that I have rotated this. Again, let me go ahead and store this in a new one, or instead of this, let me just write down show over here and let me hit on run again. So it seems like I would have to remove this equal to option from over here, and I've got this again. And as you see, initially I had a vertical image. Now I've been able to rotate it 90 degrees, and the rotation has been done anti-clockwise. So this is not clockwise, this is anti-clockwise. Now similarly, let's say if I do not want it to be 90, if I want it to be 180, let me just put down the value 180 over here. Now let me hit on run and I'll get this again. And as you see, well, my beautiful face is tilted right now. Now 180, I will make it as 270 and let me hit on run. And here, as you see, I have tilted this 270 anti-clockwise. So this is how we can rotate our image. Now let's say if I want to convert this image into black and white. Well, that is also something which can be done. So this time what I'll do is I'll write down bharani.convert, and inside this I'll just put in capital L. Let me hit on run and let me see what do we get. Well, we have this grayscale image now, and let me go ahead and store this in a new object right now. Let me call that Bharani underscore BW. Now let me show it to you guys. So I'll have Bharani underscore BW dot. I'll just use the show method. Now let me hit on run, and I've got this. As you see, initially I had a colored image. Now with the help of the convert method, I've been able to convert that colored image into a black and white image. So folks, we've done some basic image processing on top of an image. Now we'll go ahead and do some filtering on top of the image. So for this, I'll go ahead and import my required library. So here I'll write down from PIL import. So from PIL, I would need image so that I can load any image that I want. After this, I would need something called as image filter as well so that I can apply all of my filter operations. I have imported these two. Now I need to load the image. So I would have image.open. Inside this, I'll just go ahead and give in the name of the image, which would be home.jpg. And I will store this in a new object and I will call it as home. So basically done is I have used this image object and I've stored it in a new object called as home. Now if I want to show this out, I'll just have home.show and let me hit on run. And this is what I basically have over here for you guys. Now, what I want to do is, I want to add some filters on top of this. So I'll start off by blurring the image. Now, if I want to blur the image, what I want to do is, I'll just write down home dot, and here I will write down image filter, or maybe I can just write filter. So home dot filter. Inside this, I will write down image filter dot. Then I have a method called as box blur, and inside this I'll give in a blur value. Let me keep in the blur value to be 10, and I will store it in a new object called as home blur. I'll hit on run. Now let me have a glance at this. So I'll have home blur dot show. And I'll hit on run and let's see what do we get right now. Well, as you see, I've been able to blur this image properly. Now let's say if I reduce the value, let's say if I keep it to be 5. Now let me hit on run and let me also run this. You see the blur intensity has reduced. If I want to increase the blur intensity, let me make it to be 50 and let's see how does it look right now. So this is what we have, and now you see that it is even more blurred. So we have more filters over here. Now, let's say if I want this as a pencil sketch, I have this method called as contour, and I'll go ahead and show this in a new object called as home contour. Let me run. And also I'll change this over here. Let me again keep this to be home contour and I'll hit on run. And as you see, now this garden area, it's mostly a pencil sketch. Amazing, isn't it? Now what I'd want to do is, if I want to find the edges over here, and also I want this mostly to be black and white or mostly black, I have something called as find edges. I'll hit run. Let me also run this. And this is what I have. So here what I'll have is actually a boundary over here, and this is your mostly black image. Now again, I have something called as emboss. So let me write down emboss over here. Let me run this. I'll also run this. And this is, so this mostly looks like a water sketch where the only thing or only color which I've used is gray color. So this is how we can add different filters on top of our image using Python.
Also, I will say not only computer vision, you can use even our KNN and SVM also over here to identify these things. Very simple. Moving on, if you take the image of Lena, this is a very famous model. So when I was studying my engineering, all of my textbook had this image. Okay, same image used years on years. What is this? Take an image, put a filter onto that. What is this filter? Sharpening filter. Now, is this filter in sync with our earlier filter? Look at this filter, guys. 0, -1, 0. Okay, and look at our earlier sharpening filter. 0, -1, 0, -1, 5, 1. Okay, so wherever you go, this filter is going to be same. Now, what if I want to sharpen my image more? What is the possibility? What you can change here? Anybody is able to get the pattern?
5 needs to be changed to
let us say 10. Good, perfect. So just understand the pattern, you will get the processing part. Take this example, edge detection. Now, this edge detection, look at this and look at our edge detection here. Is it in sync? Not at all. What does it mean is it's not necessary always to follow the same thing. Yeah. In this edge detection, what we have done is we have highlighted the extreme edges with zeros and ones. And in middle, we are changing it to -4. Okay. Same thing if you want to more sharpen it, what we are doing, we are converting the complete third row to this zeros to ones and this to 2. Here also zeros are converted to -1, -1, and this one is 2. And these the middle one are all zeros. In that case, you will get a sharpened image like this. This is also sharp, this is more sharp. If I want to go one more level above, I could have done -2, 4, -2, 0, 0, 0, 2, 4, 2. It would give us a better one version above the sharpness. Okay, perfect. So this is what majorly in and out we do onto image processing, filtering. Now you may ask me, okay, fine, why did we do this? We did this because tomorrow you need to augment your image, or tomorrow you want to, basically compare two images. And let us say one of the images in some form, other one is in some form. What you do is you apply a single filter on both of them so that you bring them to a single level, and then you physically compare them one to one. Or you use distance formula to understand how far are the points. Okay, good. Perfect. So this was your image processing. Now let me give you one example on this. Let us say this is one image of me. Okay. Let us say this is one more image which I have taken. So this was usually, if you look at our ID cards, I don't know how many of you feel that. I have a 6-year-old ID card from Capgemini. Okay. If you look at my image before 6 years, and if you look at my image now, this is something like before and after. Something has happened to me because of which this image is in no sync with what I currently look like. Okay. So let us say this is my old image and this is my current image. So let us say this is something on my ID. This is something which live my organization is taken. Now I want to say this is old and this is current. And there could be one more image from a person who looks almost similar to me. So I will say this is a positive image, this is a negative image. Positive in the sense it is kind of me. Negative means I know it is not me. What if I take this 3 separately through a convolutional neural network? Say, what if I take this person through convolutional neural network? Okay, I will get a set of matrix. Agreed? I take this image, I'll get a set of matrix. I take this image, I will get a set of matrix. Yeah. Now, what should I do to find out that these two are same where these two are not same? I need some patterns, right? I need something, some function. What according to you could be used here?
Facial features.
Sorry?
Facial features.
Yeah, but if you observe here, these are nothing but numbers. These are just numbers, some matrices. So what algorithm or what I should use here? Guys, you remember KNN? What was KNN? Yeah, I know you know KNN. Silly of me asking that. But yeah, what does KNN do? Distance? Yeah?
Yes.
So what if I find out the distance between these two matrices? Give me 1 minute. I just have to plug in. Yeah. What if I try to find out the distance between these two? Okay. Let us say the distance between these two is alpha. And what if I try to find out the distance between these two? Let us say beta. Now tell me the relationship between alpha and beta. Guys.
Shortest distance. Between which?
See, when I subtract two similar things, what will be alpha? Can I say tending to 0?
Yes.
Yeah. And when I subtract two dissimilar things, this will be tending to infinity. Beta. So can I say alpha is always less than beta? Yeah. Or else can I say like this, alpha minus beta will be always less than equal to? Does it come to your, okay, fine. Let me not confuse you guys. What I was trying to say is, please remember at the end of the day, these are nothing but numbers. You can use any of your machine learning classification techniques to do this. Here, what I did was here I used loss function as distance. We can definitely find out the complete distance and we can say which two are nearer, which two are farther. So if I say, if we say two images are similar, I will say, let us say the similarity should be around 0.5. So when I subtracted them, no, let us say I got a value of 0.29. That means the difference between them is 0.29, which is very less as compared to 0.5. I can definitely say that the distance is very less between them. But let us say when I compared this with this, I got a distance of 0.75. It is above my threshold value. So I can say that yes, both of the images are different. You can use even CNN into that level, very simplistic way. You don't need to go and do all hi-fi stuff always. This could be as simple as this. This is called metric learning into CNN. Okay, so this is where you will need all this image processing skills sometimes to alter the data. I hope everybody is in sync with me. Yeah. Amit, Shakti, Akash, Dhruv, Harish, Kaushik, Kranti, Raghu, Vishnu. Are we good? Yeah. Perfect. All right. Great. So now let's see this case study where I'll say it's not majorly a case study, but yeah, some of the basic concepts which will help you to work on this. So what do I have? I have got NumPy. I've got SK image, okay, which has a data. There are some images pre-stored, and also it will help us to do some kind of IO functions. Okay. Next, there are some predefined data sets which are stored inside Python. So inside basically SK image. One of them is coins data. So I just have to call the data, coins data, and then push it onto image and find a type of it. So usually it is a NumPy array, because if you remember, I just said images are nothing but a matrix of numbers. Okay, and if you want to see how do they look like, first of all, if you want to see the shape and size of it, 303 cross 384 is that image, one image. This is how it looks like. So if you want to play around with it, if you want to see what is image 0 cross 0 has 47 numbers in total. Yeah, so this is nothing but your 47. Also, if you want to print the top, say print stuff from 100 to 150 on X side, and from Y side you print some from 25th to the 75th reading. If you do that and you print it out, you get an image like this, which is one of these coins. Okay, now CMap defines what type of image it is. If you want a grayscale image, you can put a grayscale here. If you want a red, green, blue, you have to define reds, greens, and blues. So I have shown down the line, or else let's do it 1 minute. Okay, so this is my grayscale. Okay, this is my image. So let us say if we say 0, 1, 123, say 0, 7, 1, for example, it's 130. Okay, so what do we do now is, let us say I want to show you a grayscale image. So I will say gray. Okay, in that case I'll get a gray one. If you want a green one, greens, we'll get a green one. Yeah, so these are some manipulations on CMap. Later on, there is one more set of image called data.coffee. So this is how it looks like. Now look at the dimension of it, 400 cross 600 cross 3. That means it is RGB kind of channel. Okay, next is if you want to focus more onto the the red part of it. So what I do is I keep the third channel as it is normal, and I say reds. So for example, if I say greens here, okay, it is going to give me a normal image when it is green, how it looks like. That's it. I'm just changing the filter. Why? Because I have not imported the image here. Okay, if I want to make it more greener, if I want to focus more on the green part of it, so what do? Say I change this. Okay, so if I want to sharpen it basically from the green side, so when I print it, look at this. If I want to make it more green, so instead of blue, I say greens. Yeah, it's going to become more sharper and sharper. So this is how we can play around with some of these numbers. say I want everything, or else say, I'm not sure, I've never tried this. Let me try from 1 to 3, say 1, 2, 3. I never altered the middle one. Yeah, good. Let's not play around with this. Yeah, so this could be some operations you could use it. Next is understanding the filters that we have shown. So this is one new image, and this particular image, if you observe, if you want horizontal bars, so this is the same image as this. The only thing is we have got a filter here. If you want to sample it, or if you want to edge detect it horizontally, the first and the last one, horizontal one, should be -1s, other one could be 0 or 1, not a problem. If you want to do the same operation vertically, common sense, the first and the last column should be -1s, other one should be 1s. Okay, what are we doing? Basically, we are multiplying this with our image. That's it. Next is, if you want to sharpen if you want to edge detect it properly. So if you go to our PPT, the same filter is used for that camel. -1, -1, -1, -1, -1, instead of 8. So let us say if I do 16 here, for example. Yeah, we have got back the original image almost. What if I reduce it to 2? Yeah, so at 8, perfectly it detects all the images, and it does not show me black and white. You can easily see there's an 3D kind of cubes over here. Yeah. Second thing is, if you want to blur an image. So if this is my original image, and if you want to blur it like this, what you have to do is you have to multiply, or else you can say you have to divide something by 16 and multiply with an identity matrix. Or I will say not even 16. You can take any number here, say 1 by 5. Definitely you are going to get a blurred image as compared to this. As you keep going higher and higher, your blurriness is going to kind of vary. Yeah, good. So this is what it is majorly onto your image processing part of it. Play around with these images, import your own image, and try to play around with these filters and all. You will get to know. Now, one quick question is, sometimes we are using 4x4 filter, sometimes we are using 3x3 filter. Okay, do not hesitate to use even 8x8, nothing wrong into it. The only thing is, you have to know if you want what kind of feature you want out of it. That's it. Yeah. There could be many websites where these standard filters are defined. So you can download some of these filters and try to create your own values out of these images. Play around with that. If you're not able to find them on web, do let me know. I'll try to search for it. Okay. Good. So you can do some work on image, understand what it is. Now moving on to something complex now. So let's see how to do all this now, how to go ahead and can do convolution out of this. So these all are the basics. Yeah, so just observe the animation that is happening on the right hand side. So on the left, we have got 3 bigger images where we are convoluting them layer by layer. So the first one was layer 1. Now we are doing layer 2 convolution. And finally, you will observe the green colored cells. These are the final outputs of your images over there. Okay, guys. And also you observe the right hand side how RGB is working onto it. Okay, so any image is nothing but a combination of RG and B, 3 layered, and finally we are convoluting it and converting them into one particular value. So here 4x4 is getting converted into one particular value. So we are convoluting the image. Okay, good. Now moving on, another simplistic version where you don't need to focus on all of them. So if you observe in our previous animation, we were going cell by cell. So if you see, we did not move anything extra. We are going to almost all the cells. Did you people see that? Yeah. Here, what are we doing? We are not going to all the cells. We are going to some focused areas, for example. Yeah. Now, how do we do that? There is some factor called stride. If you guys have seen your weekly videos, the professor talks about something called stride factor. What is stride? Very simple. If I have this, say 4x4 image, Okay, just assume this is a 4x4 image. And if I have, I'll take a red one and I'll take a dark color. If I say I have a 2x2 filter, this will be my first filter. If I say my stride is equal to 0, that means I have to immediately go to the next. But if I say my stride is equal to 2, so what I will do is, let us say this was, initially it was intended like this. Now, if I say my stride is 2, I will skip 1 and 2. I will go to the next one. So in this case, it's not possible because it's not there. But what we'll do it, just imagine there was one more column. I will skip 2 cells and move on to the next one. So these are the examples where you can increase the stride and focus only onto certain patches of your image. You don't have to worry about the whole thing. Okay, good. So this was your convolution, guys. Anyway, still this is basics only. I'm just making you comfortable with it. Now comes the real part: how to decide number of filters and this size and that size and all that. So please remember, you see two formulas here. One is called output width, one is called output height. And as I said, we'll go in reverse direction. Okay. So first thing is what output you need from your convolution layer. First question. So let us say from this whole image, if I just focus on this tires and let us say this door, it will be enough for me to identify that this is a bus. Okay. Now, that's not a problem here. The problem here is how to decide what filter size I should take about. So the first thing is, I want to say, I want to understand what will be output. So what you guys do is either you fixate on this or you fixate on this, whichever way you like it. We cannot have both the options. Say I fixate on my filter. Say for example, I use 2x2 filters 4 number of times, 4 filters out of that. My stride is equal to 2. That means I will skip 2 cells and move on. I don't want to do a very good sampling. Yeah. For that, what I will do is I'll take the width of my image, which is 32. Okay, minus width of my filter, which I have decided as 2. So 32 minus 2. So let me do it properly. 32 minus 2. 1 minute. So I will reduce this thickness, otherwise I will not be able to write. Width is 32. What is this width? Width of my image. Okay, a minus width of my filter, that is 2, plus 2 into padding. Padding in the sense, sometimes the image is not enough to scan because of our filter. We just saw just now when I was trying to do stride 2, it went out. So for that reason, what we have to do is we have to pad it up. Pad means add an extra layer of zeros around it. In our case, we don't need padding. So this will be 0, I will say. 2 into 0 is 0. Divided by stride. What is my stride? Stride is equal to 2. If you compute this, 32 minus 2 is 30. 30 by 2 is 15. 15 plus 1 is 16. This is how I got my convolution layer. Now, what I did was I froze this and I got this. What if you freeze this and you can get this? How? It's very simple. You say 16 over here and don't put anything here. So the equation will be 16 is equal to 32 minus filter width plus 2 into 0 divided by stride I have set as 2, okay, plus 1. Take everything on the other side, you will get your filter width. So it will be 16 into 2 is 32. 32 is equal to 32 minus filter width plus 1. So I will set 33. Sorry, divided by, sorry?
First, I think you have to take +1.
Yeah, I did not take the LCM. Okay, now it's okay. Yeah. So 32 plus 2 is 34. So when 34 goes this side, it will become minus 34. That will be minus 2 is equal to minus of f of w. Minus minus cancel. So I will say my filter width is nothing but 2, which is nothing but your answer. So whichever way you do it, I'm okay with it. Yeah, you can check it up with this. Guys, quickly check it up. Is it matching here? I will not do it. You people compute it. Both the ways. Just check it out. Is it matching? Are you able to do it? Padding is 0 in this case, okay? So don't take padding factor.
Yeah, matching.
Matching, right? Good. So what if I would have taken 3 cross 3 then? Can somebody tell me the output layer width?
What 3 cross 3?
The filter here, instead of 2 cross 2, Let us say I have taken 3 cross 3 as a filter. Now what will be my output width?
Will you need padding first?
Yeah. So let's check it out. How will we do it?
It's an odd number, so can't compute.
Okay. 32 cross 32 is too big. Let me not confuse you guys. Let us say this is a let me put some brackets over here. Say 1, say 2, 3, 4 and 5. Okay, similar to that, 1, 2, 3, 4 and 5. Good. Now what should be my filter size? Such a way that, or else I will give you the filter size. Let us say 3 cross 3 is my filter size. Can you people tell me the output form? What output I'll get? What cross what? Use that formula. I'll give you 5 minutes. Just check it out. It'll be good, guys. You'll be able to, visualize the same thing in your convolution also, because you have to put hyperparameters there, right? What should be the width? What should be the size?
5 minus 3 plus 1.
Okay. 5 minus 3. Okay. Plus 1. Padding should be 1. What?
No, 0.
0, right? So 5 minus 3 divided by 2. So that is 2 by 2. That is 1.
Okay.
So what will be the answer?
2.
I want M cross N. You guys can type it out, not a problem. Type me on the chat one by one. I'll put the formula for you guys. Output width, okay, is equal to the width of your image. There's a lot of noise. Guys, please mute up. Still a lot of noise. 1 minute. Who is it? Yeah. Okay. So width of the image minus filter width plus 2 times padding divided by stride factor plus 1. This is the formula for output width and output height, both the same formula. Now tell me, guys, what will you do? You have to decide on padding, you have to decide on stride. How will you do it? Stride should be 1, stride should be 2, what it should be?
Yeah, if padding is 0 and stride is 2,
Okay.
then output is 2 cross 2.
Okay. So one answer I got is 2 cross 2. Okay, perfect. So did you see 5 cross 5 image? Now we've got the best features out as 2 cross 2. Okay. Next, anybody else? Change the padding and stride. Check it out. See, guys, what here Dhruv said was he doesn't want to do any change in the padding and also doesn't want any stride. So sorry, stride is what, Dhruv? 2, right?
That is 2. Yeah.
Okay. In that case, you can say this is 3 cross 3. And if stride is 2, 1 and 2, it will come here as 3 cross 3. Then in the next layer, 1 and 2 will come like this. Agreed? And it will come like this. So do you people agree it's a 2 cross 2? Perfect. 1, 2, 3, 4. Because he has taken stride as 2. What if the stride was not 2? Then in that case, what will be the answer? Let us say stride is 1.
3 cross 3.
3 cross 3, exactly. So you will get more features, 3 cross 3. What if you take a padding, Dhruv? What if there was a padding there? Let us say I take a padding of...
If we take padding and 2 stride, it gives 3 by 3.
Okay, perfect. Perfect. So now I hope you are able to get it. It is not always necessary that to pad or to have more strides and all. It all depends on your filter. So you baseline one of them. Either you baseline this or baseline this and then choose the other one out of it. I will always say baseline this. Easy way. Okay. Is everybody in sync with me? Everybody got this, guys? From next week, we'll not be able to discuss all this. Okay. So when I say something I've taken in the code, you people should be able to identify what is stride, what is padding, how I've taken this decision. Okay.
Padding and stride are
So
hyper.
yeah, kind of, yes. Anything else, guys? Anybody wants me to repeat? No? All right.
If padding is 1, then what will be the effect on actual image?
See, if padding is 1 through, padding is like putting zeros. So you will get one extra white colored patch onto that. That's it. I will say padding personally is not good, but sometimes our images are of some odd size, no? To match up the filter, we have to do padding. Correct?
Okay.
Yeah. It is like a fake white colored layer unwantedly pasted onto that.
So Krishna, padding would be used if the image is not like in square in shape or something.
Correct. Agreed. So here we have taken 5 cross 5. Now what if it was 5 cross 6? So let's try that out. And guys, remember, it's very difficult to visualize all this. So don't strain yourself if you say, okay, I'm not able to get it. Definitely one shot will not be able to get it. Say this is 1, 2, 3, say 4 and 5. Okay. Now if this was 5 cross say 3, for example, 1, 2 and 3. Okay. Now my intention here is to use a 3 cross 3 filter. Is it possible? First of all, just check it out, guys. A 3 cross 3 filter, how it will look like. So let me increase the thickness. So it will be 3 cross 3. Yeah. And if I say stride is equal to 1, now what's going to happen? To have one more 3 cross 3, do I have space? No. So in that case, what I have to do, I have to add one extra padding layer on the whole image. Okay. So usually you will see in all the codes is usually by default they take a padding of 1 or 2. It's okay. Because we are not sure, sometimes we'll not be able to visualize this. So it's okay to take an extra padding, doesn't matter. Sometimes we don't do it. If we don't do it, if it is an issue, it will throw an error. Anyway, it will notify us. So once it notifies us, either we change the size of filter or we change the size of image immediately. Good. Vishnu, is okay now?
Yes.
Got it? Okay, perfect. Okay, so moving on now. So this is very important. Please remember, so when I share this, keep it with you, and this is very handy also. It's not a big deal. Okay, so this is what is padding. What it will do is it will unwantedly add an extra number. Usually it is zeros, so it will not impact us much if we do pooling. Because if you remember what is pooling does is, pooling will pull out the best feature. So if I pull, let us say out of this, anyway the 0 is going to be ignored somehow. Okay, so it will not affect much, but at least it will not hinder us from doing. Yeah. Next is pooling layer. So we have 2 types of pooling available. I will not say that's it. You can have your own version of pooling also, but these are the most popular ones. Max pooling, average pooling. So average in the sense you take average of all 4 of them and you pull as one number. Max is take the max of it. So in this case it will be 112. Okay. Good. Yeah. Guys, one more thing. Sorry. This is the max pooled image. From here it is got. So if you see 20, 30, 37 and 112. This is how we got. If you still want to max pool this further, then answer is 112. Okay, I did not see that. I'm sorry. This is coming from here. Okay. This one also, if you observe average pooling. So take an average of the first one. Let's check whether it's in sync. 20, so 32, 40, 52. 52 by 4. Correct? It's 30. All right. So what else we can do? Anybody? Any idea? We can use any other computation.
You could do min pooling too. I mean, since we're doing max.
I mean, see, here we want to extract the best features. For mean pooling, you're saying we'll extract the worst features. Okay. If in case we want to blur an image, let us know. We can do that. Okay. Let's see. Let's see that. I've never tried it out. Okay, let's see that. But yes, if you want to spoil an image, if you want to spoil certain part of an image as a blur part or something, yeah, you can take that mean value also. Good one. Anything else out of these four numbers you can?
Can we take
Sorry?
min max?
Min max. How do we do that?
Or we can take a kind of maximum value minus the mean.
Okay, perfect. Perfect. Let us say in this case it will be the 20 minus 37. Okay, nothing wrong. Yeah, but you have to design your own. At least it will not be present in the standard function. So you design your own function. The standard values are these two: max pooling or average pooling. Good. So that's it. Yeah. So now how it looks like. So a fully connected layer. So what do we have? We have got your
Hey,
input.
Krishna, one
Yeah.
quick question.
Yeah.
So where do you use max pooling versus average pooling? I mean, how do you make that decision?
Okay. See, use max pooling onto, let us say you have a low sampled image. So let us say the sampling here is 2 megapixel, for example, and the sampling rate here is 16 megapixel. In that case, what's going to happen is the images which are nearby, they'll be almost similar itself. So in that case, you can take an average, not a problem. But if you feel the sampling of your original image is not that great, you do max pooling. Extract the best out of this feature.
Okay.
Okay. See, I'll tell you why. Let's go back.
Are you saying that if the image is higher resolution, then go for
average,
and if it is lower resolution, then go for max? Okay.
Correct. See, if you look at this one, okay, this is only 0 or 1, or I'll say black and white. So now, if I have a filter which is focused onto this, which one you think is of our importance, guys? Max pooling or average? Max. Correct. We need to know where there is a black pixel. Definitely, we are going to get this. So this 2 cross 2 image now is represented by 1, which is called black, which is nothing but black in number. Now let us take one more example. Say, for example, you are having your stuff into this. Now, what is maximum number over here? All of them are ones. So if you do max pooling onto that, what you will get? 1. Or if you do, let us say, average onto that, what you will get? Average is
3 by 4.
3 by 4.
0.7.
Correct. So you can do this or you can do this. So anyway, the answer is we got to know that majority of the features over here are 1 itself.
Yeah.
We know that. So this is some example of average. This is an example of maximum.
So I think the other difference is if you do average pooling, then especially where, for example, you have four black. I think that difference between the different values would be more of a range.
Okay. Let's take an example. Say, where do we get 4? Here we don't have it. So let us say we take something like this. Yeah, we take something like this, 3 cross 3.
Yeah.
Okay. So if you take an average of this, yes, I agree with you. Yeah. Kind of. Yeah. Works out. So we have got 1, 2, 3, 4, 5. 5 divided by 9. That will be our average. Yeah, correct. Okay, good. So it's, guys, you understood what is he trying to say? He's trying to say that you will exactly get the number. How many blacks are there? How many whites are there? That's it. 5 by 9. So the denominator is nothing but your total number of whites available out of 9.
Yeah. So the reason I asked that is, so in essence, you are getting more information, right, into the next layer or into the next.
Correct. So we are basically taking the best information out of this and moving ahead. Here in our case, guys, best information means black. Worst information means white. That's it. You don't want white out of this. Now, are you guys comfortable a little bit with the filter part? Now you get the point why we need filters, what filters can do, and what axe pooling will do. We just need the best features. We don't need extra background stuff from this image. Let's not do it. Good. So this is one way to represent an image. If you want a little bit more simpler version, you can do this. What I feel this image is a better representation of where you can take out certain features out of an image and directly classify that it's a car, truck, or van. This could be a we will see this little later in our course. We don't need to go and scan everything. Certain features will take it out completely. Okay. Good. So this is an example I will say of RCNN, Regional Convolution Neural Networks. We will see down the line. This comes in around third or fourth week. Good. So we have done almost everything which was needed. So next session, what I will do is we will start with implementation of the CNN, and then we'll move on to a very simple topic called transferred learning. So just to give you guys a very clear, a quick 5 minutes idea onto next week's videos, don't worry. Those VGG, LXNet, FlexNet, then ImageNet, ResNet, all those nets that are produced, no, they are produced by some people who have done a lot of permutation combinations to find out the best combinations of convolutions here. You know what it does? It basically, whatever image you give, no, it tries to classify you properly. Now, what has happened since these neural networks have one certain computations, they are standardized now. What does it mean? Their weights are stored in an HDF format. Now on, what you can do is you can build up your code. You can download their weights. You can ready the architecture for them. You can automatically download their weights, and you can build your own FCNN at the end. So whatever you download, no, that will be only convolution neurals. The last layer, the last 3 to 4 layers that we are supposed to do, our own layers, that is your fully connected neural network layer, is what you have to design. That's it. Your network is ready. You don't have to take a pain of building your own CNN. This is called transferred learning. That's all is the topic for next week, whole week.
So which means the weights are already initialized?
Yeah, already, not already initialized, I'll say. The weights are already ready. The filters are already ready. All you need to do is pull it down and then rerun it. See, it's like you cannot train them. You can train this. So when you do your fully connected neural network, when you train your model, these are non-trainable static stuff. This will be your trainable stuff. That's it. Do you think our problem will be solved? Yes, right? You don't have to take a pain of designing a very complicated neural network. Neural network is good. We get it. But you don't have to take a pain of designing all this. You are getting this ready-made, this part. This one, what you are supposed to design. And you people are very good at this now. Got it? This is called transferred learning. It's like one of you design a code, generic code, and give it to all of us. We just change the input data and run it as our classification model. That's it. So don't get confused if the professor is showing LXNet. LXNet is very big. You just have to understand that this is a ready stuff. We are importing it and running it on our model, so that I don't have to go through a pain of training my own model. And usually the parameters are something like 6 million, 10 million, 16 million parameters. That's the reason we don't need to train them. We have to directly get them. Ready-made tools.
Krishna,
Right?
can you explain with an example? I mean, so would you say that maybe you have a corpus of vehicles, right?
Yeah.
So you would get kind of a model which already can identify vehicles. Correct. Because it has learned, it has gone through a corpus, and then you just add maybe a few more layers on that just to look at maybe if your problem is to identify a Ford vehicle, then you work on that. Is that the way?
Correct. See, Vishnu, have you heard about framework anytime in
Yes.
our industry? Yeah, what's a framework?
Framework is basically like a guideline of how to do work.
Yeah. Okay. So for example, let us say you are doing Lean.
Maybe skeleton, something like that. Yeah.
Okay. Or let us say, have you heard about A3?
A3, no.
A3 implementations under Lean. It's a framework.
Okay.
Let us say you have a service and you want to improvise your service. So what do we have? We have current scenario. Let us say what is the service's current scenario? What is the problem you are facing there? How you intend to solve it? And what is your timeline to solve it? Let us say there is one framework available to us. What you need to do when I give this framework to you, all you have to do is you have to put in your data. That's it.
Yeah.
Correct? Something like this, you can imagine that there is a neural network which has its own corpus, which was trained long back, which was approved by a lot of data scientists long back, which kind of is similar to what you are doing. Let us say the corpus over here was a lot of image or object identification. Any kind of object could be identified. Now we already have this neural network ready. So what these people have done is they have actually frozen their weights for us and converted them into an HDF format.
Okay.
Now what do? I take these weights as our framework. And now I just put in my data onto that. That's it.
Okay.
And use them. That's it. So I'll give you some of the popular ones which I am comfortable using is VGGNet, MobileNet. So what is MobileNet? You use it every day on your phone. If you people observe, your phone tags your face. It is not possible to put very heavy stuff on your phone because of computation. So we have simplified VGG into a very lightweight model called MobileNet, and we are using this ready-made. You can use ImageNet. You can use ResNet, ResNet. We will see down the line what are these things. But in the next videos, you are going to see this. Okay, good. So the video next week should be very simple. So once you have got the concept of filters and convolutions, next week should not be a tough one. All right. Week 1 I feel is the toughest, and week 5, 6 I feel is the toughest. So middle of these weeks are pretty easy. We should not be a problem. Okay. All right, guys. So I think I'm done. If you have any questions, do let me know. Else, let's close down.
I want to ask one question on the project because I think when I was looking at the data, there were some missing values. So for neural networks, do we need to do any imputation?
No. Missing values in what? Images.
I think there was some data also that was provided in one of the case studies, I guess.
Okay.
And it has many n values. I'm not sure if it was that project only or if it's
No.
a different project.
In this project, there is no missing value. And there is no imputation to be done. Okay? Yeah? Good. Okay. Before moving on, I just wanted to ask you one simple thing. Let us say I have an image, which is, say, 64 cross 64. Okay? And over here, I have a neural network. Say the neural network is having 512 inputs, for example. Okay. And I will say again, they have their own hidden layers. And finally, we are converging this neural network to say one classifier over here or 2 classifiers. We don't care. So the pointer over here is we are supposed to input 512 inputs. My current input is 64 cross 64 cross, say it's a grayscale image, so 1. Can you guys help me to put how many convolutions I need and what will be the size of my filters, max pooling and all that? Can we do this quickly so that I get to know that you people are in sync and we can go further onto this. So let's start putting the blocks over here one by one. Yeah. Okay. So let's put the first block. So what I'll do is we will write the filter size over here, filter size and max pooling, and finally we'll put here what is the total number of we have got over here. Yeah. So let's start. How to do this? How to design this filter?
3 cross 3 filters.
Okay. So we'll start with 3 cross 3. Okay. And how many I need? For example,
64.
So how do you decide on that? Okay. So yeah. So one hint from my side is this particular term we have no clue onto how many we need and all. So for now, you keep it empty. It's okay. But at least let us say you have decided 3 cross 3. So if I have 3 cross 3 here, what will be my output here? So what will be the output of my, what do you say, filters over here?
So it is 64 plus 3 minus 1.
Sure.
Yeah.
Okay. What is the formula? Width of the image minus width of the filter plus twice of padding divided by stride plus 1. This is the formula. Okay.
Okay.
Yeah. So now start putting it. So first of all, I will say, okay, stride is 1 only. I'm not changing my stride. And padding I have not done. 0 padding. So what will be the size here?
So 64 minus 3 plus 1.
Correct.
62.
64 minus 3 is
61.
61. 61 by 1, so 62. So I can say the output that I'm going to get will be 62 cross 62. Now, if you look at this and if you look at this, it does not make much sense to me. Why? Because we have not reduced much. So to reach to 512, so 512 means when I multiply these two, I should get 512 somehow. So if you multiply 64 and 64, you are going to get 4096. Yeah. So this particular thing is not going to help us. So in that case, what do I say is this transformation is not that great. Now to reduce it, what I will do is either I'll increase the size of my filter. It's not fair. Or else I will increase my stride. So let us say I increase my stride to 4. Okay. Now can somebody tell me?
So it's an odd number.
So
Odd divided by 4 is point values.
64 minus 3, or else let's be fair. Okay, 64 minus 2, 2 cross 2 will do, no problem. So 64 minus 2, that is 62. 62 by 4, that will be 31 by 2, that is 15.5. So say 15 will take. So 15 plus 1, 16 cross 16 we can get. So that is a good transformation. So now what is the problem here, guys, is this is not an easy task to do. So on purpose, I took these numbers so that it is not an easy task that, okay, I have these things in my mind, I have some input, let's try to convert the input to something. And also it is not easy to decide how much is the size of the filter, what will be my padding, what is this. So it is good to know the formulas and do convolution onto simple images. But when you go on to larger images, say 1 megapixel image, for example, and if I ask you guys that, okay, my image is 1 megapixel, can you design a CNN for me, which should intake 512 over here? So it'll be, you can do it, not a problem. You will be able to put one by one all the filters, or else even you'll back propagate and try to change and all. Good thing, nothing wrong. But it'll take a lot of time. So to avoid these confusions, what we do is we use a concept of machine learning. Concept of transferred learning. I'm sorry. Now, what we do in transferred learning is, let's try to see that. Can any of you name one library from machine learning which is the best, like which has almost all the algorithms or all the functions that we dropped? Like I'll give you an example of SVC or KNN or decision tree or random forest. Which library we used for?
Scikit-learn.
Scikit-learn, right? Let us say we use that library to do that. Now, what is exactly scikit-learn? Can't we program a SVC using for and if loops? We can easily do that, right? But why don't we do it? Why? Because we already have a function, somebody has returned it, somebody has coded it in a generic way such that it will help us to input our unique data, and according to that, we'll get a customized output. It is solving my purpose. So what we do, we call this. Now, when we call this particular thing, what are we doing? We are getting the stuff ready-made from them. We are getting the hardware ready from them. The only thing is, we are getting the infrastructure ready from them. Only thing what we are doing is we are putting our data. That's it. Now, keep this in mind. Let us say there are certain readily available convolution networks. I'll show you down the line which all are there. But say there is one convolution network which is readily available. And say you have stored the weights of these functions in an H5 file or HDF file or whatever file we have pickled all of these weights. I'm not saying the entire network, I'm just saying the weights of the network. Weights in the sense, what is the size of the filter, and what is whatever we saw in the above example, which we kind of if we're not able to clarify, weights are there. Now what do? I ask or I request this particular model to import the weights to my model. So let us say this is your model. You have created an exact replica of this model. Now what you do is directly pick up the weights and drop it in your infrastructure. Okay. Once you drop it in the infrastructure, what is remaining now? So you have just got convolution weights. What you have to do now? You just have to build your FCNN here. That's it. Fully connected neural network. We can easily do it, not a big deal. So this is what we do on the industry side. We do not write much of the CNNs. And even if we are successfully able to put a CNN of our own, training it and correcting it will take a lot of time, to be very frank. So I will say majority of your implementations on the industry point of view, you will be using transferred learning. But in this certification, at least for 1 or 2 or I think 3 weeks, we will be handwriting some of the CNNs, and after that we'll start picking up CNNs of our choice as this. Okay, and that example that we saw, we will see it in the code. Let's see how we can solve it up. Okay, any questions on transferred learning? The concept part of it, I will show you how we do it, but this is what overall goes around. We directly take the weights and use it. Okay, any questions? No?
sir.
Perfect.
No.
All right, good. So now let's try to use a PPT. So today I will use one PPT where they have mentioned a lot of networks. Now for first point, it will be very confusing immediately. So don't expect, I don't expect you guys to master this networks in one module itself. What we are going to do is I will pick up each network every week. So let us say in today's session, I will pick up VGG, which is the most important one. Probably next session, I could show you something on LX, something on LENet, or I can give you something to do on LE. And post that, we can go to the complex networks like ResNets, Google ImageNet, and all those things. Okay, and this is not it. There are so many available. Okay, so let's start. Yeah, so for today's agenda, we will start with CNN architectures. So we just took an introduction of what is CNN. CPU versus GPU, we know this. I'll not go in much detail. And the most important, transferred learning. Now coming to the architecture of CNN, try to push our formula here, whatever we saw, right? So Harish, I think this will solve our problem, except I will say it will not just solve the problem of what is the math behind selecting the number of filters. I'm still working on this, guys, and give me a week's time. I'll try to find out some paper or some logic behind this.
Okay, Krishna.
Yeah?
Yeah, okay, Krishna.
Okay,
Even
so,
I will search for that.
Yes. And also I will request our great learning, I think the professor who is teaching this, if he can share some papers with us. So Frank, so far I'm not able to find any particular good reference where I can say that this is the math behind selecting these filters.
Maybe what I feel is, as you said, they have also decided first what is the final fully connected layer, and then they decided on this number 6.
Reverse engineered it, right? Yeah.
Maybe I also think that, but
right.
I'm not sure. Yeah.
But still, there should be some logic, because randomly I cannot put anything here.
Yeah.
I feel it is a little weird. Okay. Also,
Yes.
I tried, see, if you see here, what does it mean is we have 28 cross 28, 6 filters. So what if I multiply 28 into 28? Okay, so let us say I have 32 into 32. Now, when you multiply 28 into 28 and then add it 5 or 6 number of times, I'm not sure we are going to get the same number back, to be very frank. So what is happening is, as per our analysis or as per our knowledge in CNN, what is happening is we are converting, say, if the stride is 1, then definitely you are going to have the network which look like this. So one particular image is getting converted into many features. That's what the 6 thing shows. So I used to take it as feature maps. I used to say there are 6 feature maps available. That means I can pick any one of them put it to one of my convolution network, fully connected networks, and try to find some information out of this if possible. Okay, this is what I used to take, but now I feel that is not enough. I need also to know how to do this. So apart from this, in today's session, let's ignore this. But apart from that, you can directly see 35 minus 5, that is 27. We are saying stride as 1, so divided by 1, padding is done 0, plus 1. So if you look at it, 28 is the 1. If we still do it, 28 minus 2 divided by 2 plus 1, you are going to get 14 out of it.
Yes,
The
yes.
formula holds pretty good onto this part of it. So at least 50% of the stuff is solved. Except now if you ask me, okay, how they came up with this network now. So I will say it is a lot of mix and match trials happening. So it's not a one-shot job that, okay, they decided this and they got the best accuracy. Because if you look at it, they are currently working on 60,000 parameters. Okay. Now what are these networks and how we can use it? So if you look at the highlighted area that I am just drawing, this is what I am interested in. So if I have a ready-made network, open source network for all of us, which can identify handwritten digits. So your neural network project, if you remember, 7, 6, 5 and all. I know they were not handwritten, but anyway, we can correlate this. If I can do this, what I can do is rather than writing KNN, rather than writing the neural network, what I will do, I will ask this LENet weights to be dropped onto my network and then design my own fully connected neural network depending on how many number of outputs I have and take it forward. Okay, so these are the features. Now, if you expect to use the readings onto a face recognition system, then it will not work, to be very sure. Why? Because please remember, this is what is important. So why am I specifying is tomorrow when you're picking up this, you should know what it will solve. Okay. All right. So this is it.
This only works for the handwritten digits. Nothing else we can apply.
Yeah. If you are importing the weights. Okay. If you are replicating this network and giving face as an input and trying to get an output and just check how it is. If you get a good output, then you can say that yes, it works for face recognition also. Correct? But for importing weights, it works only for handwritten because they are trained only on that data.
Okay. So it means like if we are using it ready-made, then we can apply it only for the handwritten digits. But if you are trying to replicate the same thing, same architecture, then we can provide the face as whatever inputs we can.
Perfect.
Correct?
Perfect.
Okay. Yeah.
Perfect. So when I deliver today's code to you guys, no, so in today's code, we are going to use VGG. We are going to import VGG and do it. So what you guys can do is you have the network in front of you. You pick up your older data, that MNIST or SVHN data from your previous project. You pick it up, try to replicate this network and see what you are getting as an output. Simple. Okay. So how do you replicate? You use the same values. And at the end, when you're connecting this fully connected neural network, you multiply these three. That's it. That will be your input. As simple as that. Or else, if you don't want to multiply all three of them, 5 into 5, 25. And you give 25 as your batch size. Okay. So at one shot, 25 will be picked up, put it in and moved out. Or else if you want all of them, all the filters to be put in at one shot, you can do that way. Or else you can pick up one by one and do it. Yeah. So try this out. Good. It's good if you play around with this particular network because it's a very basic one. So if you're good at this, then you will be good at the next one also. So if you look at the features, it is for handwritten. It was published in 1998. So I will say it is an outdated algorithm, but I have used this into multiple tasks where I have to identify simple digits. It works perfectly good. No problem at all. Yeah. 60,000 parameters. If you are looking at your current collab, then I will say it is not a very big network. If you're looking at Jupyter, yes, I will say it is a little heavy on Jupyter. The dimensions of the image decreases as the number of channels increases. So if you observe, the dimension is decreasing, but number of channels is increasing. Or else I will say rather than channels, what happens is when we say channel, we get confused with grayscale and RGB. Another case, I will say, call it as feature maps. So each square that you see 5 cross 5 square carries some kind of feature. That's what it means. The activation function used in the paper was sigmoid and tanh. But now what we do is you don't have to use always sigmoid and tanh. You can use ReLU now. You can replace both of them by ReLU. No problem. It will work good. All right. So this was your, how do you say, this network. Okay. Moving on. Okay. So some pointers here is it's a 10-way neural network classifier. It works properly on 0 to 9 data, handwritten digits, tolerant to various transformations like rotations and scale. So if you do augmentation also, it's going to work good. So our SVHN data will work pretty good onto this, no problem. Was used by banks to recognize handwritten numbers and digitized checks. So still on a very basic level, yes, they do it. So what they do is if there is a check, let us say return, if there are certain numbers written on the check about what is a payment, then let us say there is a signature over there or something. In those cases, if you want to identify the digits or if you want to identify the check number or the date, you can easily put the check below the scanner, you can pick up the data and process it. Very simple. You don't need a very heavy hardware for this also. And it's a 4 weights layer. So if you observe here, 1, 2, 3, 4, 4 weights. Okay. Now, if you guys have understood this, one quick question for all of you. Can somebody tell me if I put an Adam as my optimizer, let us say ADAM, Adam. Adam is going to work on this or on this. Take some time, think about it. How my back prop is going to work. Is it going to work on only fully connected or it's going to work on everything?
I think for everything.
Perfect. And what if, Dhruv, I do, okay, so in the first case, if you are using the whole network as it is, yes, back prop is going to work for both of them. I'll show you how back prop works for this. You people know how back prop works here. Okay. Now, leading to this, another question. What if I import the weights to my network and I use my own fully connected neural net and go further? So in that case, back prop is going to work on both of them?
No.
No. You got my question? Let me repeat myself. What if you have imported? So this is my import of weights from the LENet website to my network. And after that, I'm building my own fully connected neural network here, something like this. And now if I put Adam, Adam is going to work on this, or Adam is also going to work on this also.
I think it will work only for that part which we have customized, not for the imported part. I feel so, not sure.
No, perfect answer. Why? Because if I back propagate and if I change my weights, there is no fun of importing the weights. Why we imported the weights? Because they were standard weights. These were already learned weights. So if I back propagate here, it's not going to work out. So we have to make sure that if we do it, we freeze these panes. Whatever we have before this, we have to freeze them. They are not editable. And this side will be editable. So I think in 3rd or 4th week, I will show you how to do that. Yeah, but this is a very generic question. So when you go for an interview or when you look at some of the most important deep learning convolution or CV questions, this is what they ask. Okay. So this is one concept. Now, keeping this in mind, let's try to complex, or let's try to make one more model out of this, which will be your LXNet. So LXNet is an extension of LENet, we can say. And why do we need this is, let us say the earlier one was able to identify 0 to 9. What if I want to identify some of the objects or some of the faces or any other thing which is not even number, which is more than a number? If I want to do that, I need a bigger architecture. So what they have done is they have simply increased the layers of convolution and pooling. That's it. Okay, there is no other difference. And if you observe, even there, FCNN will differ because of number of changes. So the goal for the model was the ImageNet challenge, which classifies images into 1000 classes, for example. has 60 million parameters compared to 60,000 parameters. So when this increased, okay, so when this increased from 60K to this one, even the capacity to classify images increased for us. Now it could be anything. If it comes under those 1,000 classes, you can use the weights ready-made from this network to your network. It uses ReLU activation function default. And this paper was convinced the computer vision researchers that deep learning is so important. Fine, this is blah, blah, blah. And this is how they have done this. So if you want to see the tabular structure, they have taken 1, 2, 3, 4, 4 heavy layers. But if you look here, something is wrong in my diagram. If you look here, there are more convolutions. Give me 1 minute. So we have one convolution, we have one. Yeah, we have a convolution here, we have a convolution here. This is no convolution, no convolution. There is a convolution here, and there is a convolution here. So I have 1, 2, 3, 4, 5, 6 convolutions and 2 similar layers. Okay, there is no change over here. All right. So this is it. Okay, so this is what is your LXNet. It's an extension. Please remember this particular number. It is very heavy. Okay, let's go to the extension of, okay, what made LXNet successful? So I will say architecture, I don't believe that, because anything you mix and match, definitely you're going to get something out of it. We can say overlapping max pooling. So if you observe here, what is overlapping max pooling is, if you observe, we are not doing in middle. We are doing for one, we are doing for another one, we are doing for another one. Okay, this is what it means. You don't have to do always max pooling after convolution. ReLU function was universally used. It is very simple. Dropouts, cropping, data augmentation, and inference augmentation. So inference augmentation, I will say, is okay. Let us today take the case study and revisit this particular part of it. But more or less, if you look at the important part, this is what it solves. This is okay. It's not a big deal. Not a big deal. Yeah, this is what you need to remember about max pooling. You don't have to do always. And I think architecture, fine. So these are some important success factors of LXNet. Okay. Next, coming on to VGG. Now, increase still more number of pooling and convolution layers, you will end up with this particular network. And let's confirm what was the image size here, 227, 227, 3, and this was 9261. And here we have 224, 224, 3, and fully connected is 4096. Okay. So if you observe, again, what you do is you increase the number of convolution layers, modify LXNet to make something called VGG. 16 is not the latest version now. Now we are having 19, but both of them work equally. So for me, if I've done some implementation, if I'm using VGG 16, it gives me a good accuracy. I don't go to 19. It's okay. 19 is a little heavier than 16. Yeah. Otherall remains the same thing as our LXNet. No change after this. So what are these what are these networks? There were some challenges in which some of these people came together and built this up. That's all. If you ask me how, it's about mix and match, to be very frank. Yeah. Okay, this is of no use. Some of the important things is from 60 million, now we are jumping to 138 million parameters. Yes. It holds a total memory of 96 MB per image for only forward propagation. Most of the memory are in earlier layers. So if you just observe that you have two things, one is your network and one is your FCNN. So we can say that most of the memory kind of goes away here. This is the heavy part, this is the lighter part. Okay. Number of filters increased from 64 to 128 to 56, 256 to 512, and 512 has been made twice. So they are just replicating some numbers from the network. So you don't have to remember all this. Whenever you want to use it, just come back to this particular thing and try to replicate the network. You have the numbers ready. You just have to put it in the Keras add dense Keras. That's it. Whatever that particular command you have to use. And if anybody is interested in paper, this is the paper attached. I will say it's a little heavy, so first get comfortable with all this and then go on the paper and have a look at it. Okay. And as mentioned over here, there are two versions, 16 and 19, but more or less it does the same job. So whichever you want to use it up. Okay, good. Now comes a little problematic part. So now these were the three simple networks which we can visualize. Now comes a little different network. We call it RESNet, RESTnet. Now, my question to all of you is, what if I want to use this particular hardware, whatever we have done? Okay, it's a very good network, agreed. But now I want to use on a handheld device, and within fraction of a second, if I give an image, no, within fraction of a second, it should give me some output, or it should put a square around my face and say that, yes, we have identified it as you. Will your device be able to hold this up? Guys?
You mean computer?
Yeah, so if you have a mobile, for example, so will your mobile be able to hold this up, this heavy processing?
Maybe as you said, there is another architecture called mobile net.
Mobile net. Oh, that's why you, okay, yeah. Mobile net is an alternate version of it, yes, but let's not go there. Let's try to think what we can do here, or, okay, my example is not corrected. Let me try to create another example. So guys, let's take one more example. Let's not think about computation side. Let's say I am currently having one image which needs to be given as an input, and immediately within some time limit t, I'm supposed to get the classification output along with some tagging or some classified output. Now, as you saw, the number of layers are more over here. So we had one layer, another layer, third layer, fourth layer, like that. Let us say so many layers are there. And it is going in a sequential manner so far. We have not broken any of the sequential, flow as of such, correct? Now, what if I want to increase the speed of this network? What should I do as per you? Let us say I'll take 5 inputs from you guys. The current time is t, okay? I want to make a time period saying that t new. Now, t new should be far less than t. That means it should be faster. What should I do?
Are you talking about embedding software like Coral,
No.
NVIDIA Jetson Nano?
No. Let's not go there, Dhruv. Let's say if I make some changes in my current network, I should get some good speed. I got it that this network is very good. Perfect. We got that. I don't want to lose it. What if I am not happy with the time part of it?
So maybe to increase the hidden layers, it might reduce the time.
If you increase the hidden layers, then the time will increase, right?
Yeah, right.
But simplify the input and output also.
Exactly. So how do we do that? You are perfectly right. How to simplify this now? Distribute, okay. So Kaushik, you're talking about parallel processing, something like that? Yes? Okay, yeah. Fine. That could be a possibility. So let me write down. What if I have a parallel processing? Or I am having a Hadoop environment where I'm doing parallel processing. Okay, fine. This could be one possibility. But we are not changing the architecture, right? What we are doing is we are distributing the data. I will split my data into many and then I will distribute parallelly onto multiple networks. Okay? What can I do in my network? Okay, let me give an example. I think then you guys will be able to pull out something. So guys, let us say when this is my computer screen that you are able to see. Okay, and for example, in front of my screen, I show you half of the image like this. Okay, now as soon as you see, so just imagine that you are not able to see this particular part of it. So as soon as you see this thing in my screen, what do you assume it to be? What shape you assume it to be? Everybody will say, yeah, it's a circle. Okay, or else if I just, so in the time frame, if I am just scrolling one image onto my screen and you are able to see only half part of it, but yet you are able to describe it, right? What it is. You will have some assumption in your mind that yes, he is trying to show a kind of square. And as soon as it comes in the picture, in my frame, everybody knows, yeah, it's a square. Keeping this analogy in your concept, what if I can give some early inputs? Say that I can take up the output of this and throw it to this. So definitely it's going to go here. So let us say the output from here to it goes here. It takes some time frame t. Meanwhile, parallelly, I throw the output here also. So what's going to happen? This particular network is going to make some outputs and start throwing it in future. So till our image is getting processed here, our output would have reached here immediately. So there are certain cases where if you look at certain parts of your image, let us say in this particular part, this, I'm sorry, one of the feature map looks like this. And as soon as I give this feature map, let us say the feature map was here, as soon as I give it to the next network, and if it gives next to this network, we could be able to identify that this looks like a cat, possibly it's a cat. So till I get all of my feature maps, all of the shrinking and all, I would have easily identified this. Are you able to get it? Kaushik, this is something similar to what you said, but here we are not splitting the data parallelly. I am forwarding the data. I'm avoiding one of them and forwarding it further. Able to get it, everyone? Amit, Dhruv, Shakti, Akash, Harish, Kaushik, Kranti, Raghu, Saurav.
Yes, Krishna.
Logical? Yeah?
Yeah.
Okay, good. So this is what RESTnet does. Now the only challenge, so nobody challenged me here saying that, okay, fine, if I do that, let us say, as I said, there is one convolution layer, max pooling layer, convolution, max pooling, convolution. There are so many like this. Now what I do is, by default, there is a sequential order. Yes, it will follow when till it goes to a fully connected neural network. But if I take an output from one node and give it to say this node, don't you think the filter is going to mismatch? Agreed? So let us say this is 28 cross 28 cross 3, for example, the output. And when we reach here, it could be 16 cross 16 cross 6, for example. Don't you think this is going to mismatch? Yes or no? Because in convolution, every step we are reducing the size. Agreed? So the output of this particular one is going to mismatch with the next or next to next one. So what we do to solve this is we keep the same stuff for all of them. That means we design a network which has same filter sizes, same activation functions. All right. This is how it looks like. It looks pathetic. So if you look at it, it makes no sense as of such. But yeah, try to understand that we are giving an early output. We are skipping one convolution and we are going further. All right. So it's a very, very deep network as suggested. Because of vanishing and exploding gradient problems. Now, what do you mean by vanishing and exploding gradient problems? So I will show you down the line. So let us say I ask you, guys, you have done the model. All of you have cleared the model on statistics. Yes. The first module. Yes. Can somebody name the 3 distribution we have done in the statistical module? Can somebody name this?
Normal distribution.
Okay.
Poisson distribution.
Okay.
And there's a
Binomial distribution.
Okay.
Binomial distribution, yes.
Okay. And one more. Okay. I underestimated you guys. Yeah. Now 5.
Distribution, chi-square distribution.
Oh, bapre. Okay, good. Dhruv remembers everything. Okay, good. Okay, what if I say what were the statistical tests you people did? What are statistical tests we know here?
Two-way.
T-test.
T-test.
ANOVA.
Perfect.
Z-test.
Goodness of fit.
Sorry?
Goodness of fit.
Okay, fine. Okay, then you guys are ruining my example. Okay, see what I was trying to show you guys was Okay, good. You people remember. My other batches said we don't know. So it helped me to explain my stuff. See, what happens is, guys, when you have a particular data which is passing through a multiple neural networks, Now, let us say the data is entered here. It went through a lot of these convolution, non-convolution layers, whatever, pooling layers, whatever layers, and finally it came here. Now say you found a loss here, dou L by dou of weight 1. So let us say this is weights. So what you do, immediately you go here and change the weights. If still in the next propagation, if you are not happy, we immediately go back and change the weights. At least I can say that at least till here, if I change my weights, I'll be able to at least control them. So what do I need to say is, the weights which are there in the earlier part of the network, if you have a very deep network like this particular weights are going to vanish away. More or less, they will make not much significance to the network, to be very frank. This is called the problem of vanishing gradient. We are going to revisit this concept in NLP next module. Under NLP, we have a network called RNN, recurrent neural network. So there is a problem, same problem. RNN is a deep network where we will face the same issue. And to solve this, we use a network called LSTM, long short-term memory network. So we'll have some memory where we are going to store these weights down the line. Okay. Now, if you look at our ResNet model also, this is a very deep network. And whenever you find the word deep network, always say that, or always remember that vanishing and exploding gradients are going to be a big issue. Vanishing gradient for these people, exploding gradient for these people. Their gradients are going to go pretty high because a lot of changes will happen, which is very near to the output itself. Okay, so this is what is your ResNet. Next, I think that's all you need, more or less. Yeah, so this is what is the important points. So the architecture of ResNet 34. Now you have many versions of this. This is ResNet 34. There is ResNet 150. I have seen ResNet 50 also. The concept is changed. Only thing is the number of layers that you are going to see here will be different. The deep layers. Okay. All are 3x3 convolutions and same convolutions. No change. So we keep a uniformity. Keep it simple in design of the network because we don't want to play around, because I want my output to work on any of these convolutions. So I will keep it as simple as possible. Okay, and if you observe, there are no fully connected layers. Okay, and I think that's it. That's all. And one thing to remember is the dotted lines in this case, when the dimension. Okay, 1 minute. Where is my dotted line? Concept. Okay, so there are two things. I'm not sure if you are able to see the dotted lines. If your input and output are kind of tracing each other, that means you can switch off some of these lines. That these are optional connections that we have given. It's not necessary to take each one of them and throw it. So if you are designing it that you are surpassing only one neural network, you can have some of them as dropouts, saying that we don't need them basically. So these are the dotted ones. So we will see, I will implement one of these ResNets. It's not in our course. It's not in our standard format here, but I don't want to leave this. I will implement this ResNet and I will show you once you are comfortable with the first three algo networks. Okay, so we'll do this. Let's see how we can design and take this. So first thing is we'll do design it. Second thing is we'll directly import the weights and use them. Okay, perfect. So this is what is the expanded or zoomed version of ResNet 34. Yeah, 34 represents the total number of how deep the network is. Now, coming to how to decide how many layers to take and all this part of it. So very simple. If you have around 5 layers in your network, it's a very easy network. Okay, it's not a deep network at all. If you have around 10 layers, including initialization and batch normalization is included, I can say, yeah, it is still an easy one, but a little complex, a little deep as compared to 5. If you go to 30 and 100, these are the real deep networks, especially I'll say that this one is a very deep network. And in this network, if you are using this, you have to identify how to skip the connections because the time is going to be very long. So if you are planning to have 100 layers or even 30 layers, please make sure that you have skipping the connections, the one which you did in ResNet. So more or less, I can say these are the examples of REST nets, LSTMs, and all this stuff. Okay, and anything above 1,000 layers, I'm not sure. I've never seen in my life. What? We have no idea about it. How deep is going to be? So if you want to look at one of the layers, which is very deep, this could be an example of the inception network from Google. Okay, look at this, and they have a lot of connections, a lot of skippage is happening here. So what is it? The inception network consists of concatenated blocks of inception modules. Okay, the name inception was taken from the meme image, blah blah blah. We don't need this. Sometime a max pool block is used even before the inception module to reduce the dimension of the input. So please remember, it is not always necessary to take the image as it is. The way we used to do PCA, same thing we can do it here also. Now, have I shown you any times how to reduce the dimension in image processing?
No.
No. Have I shown you anything on autoencoders anytime? No, right?
No.
Right? I'll show you today. So
No.
if you remember, we used to do SVD, PCA, and FA, and TSNE. I'm not sure even you have done that. Have you heard about TSNE, guys? All right. I will show you one more dimensional reduction technique in machine learning today. But apart from that, if you want to do same thing in neural network, how should we do it? The first way was nothing but your convolution layer. Correct? Convolution was something like shrinking the data itself. But if you look at convolution as data reduction, there is a problem. Let's see how. Let us say this image you are having here, which is say 64 cross 64. And after convolution, before flattening, you got an image, say, which is 5 cross 5. Or I will not say image, I got some data which is 5 cross 5. What we have done, we are able to shrink this up. Okay. Now, can I use this for future processing? If I give it to one of our networks, say LENet, LXNet and all, will LENet be able to identify that this is a part of a larger image like this? Yes or no? Can I do something like this, which I call it dimensional reduction? Is it possible to think about?
Yes, we can do that.
We can do that. Okay, we got one yes. Anybody else thinks it's not a good idea or it's a good idea?
It is possible, yes.
Okay, fine. So from my side, you guys can try this out. If you can do it. If you put a FCNN at the end, yes, it is possible. It'll become your CNN again if you put an FCNN here. But what if I want to send this to some other networks? The other networks will not have the decodings here, right? You remember we have done some encoding here. We have used some filters to encode this data. Have we given them the decoder back? It is like that cipher. I'm not sure if you've heard about this. Let us say you want to secretly communicate something. So what you do is you implement your cipher. There will be a filter which you multiply with all the things and it will create some new numbers. It will look like junk data. Now this cipher, to decode this, you have to divide the whole data by the cipher again. Then you are going to get it back. Correct? Now, this is what I call it as a cipher, whatever we have done here. Are we providing cipher along with that? So tomorrow, if you want to recreate this image, use this cipher. We are not doing it, right? So what if I want to reduce the size of the image and if I want to recreate it, we should be even able to replicate it back. Okay, but in this case, what I will do is if this was 64 cross 64, I cannot replicate the whole thing back. I cannot have the whole sampling done. So what I will do is, yes, if I want to reduce the size to 50%, I will say 32 cross 32. But still I will be, let us say if the number 7 is here, I will be able to vaguely represent 7 back. This is called autoencoders. I'll show you today one implementation also. But on a very high level, this is how it looks like. And if you ask me what is present inside these networks, there are two things which is present. One is called encoding. Okay. Encode. And one is decode. Okay. Now, anybody here from electronics and communication background or communication background or at least especially DSP part of it? Anybody? Shakti, your camera is on. Huh? Yeah. Anybody from this background, or even from computer science background, you guys would have done it. Encoders, decoders, no? Cryptology or something like that.
I think I
Yeah,
have.
yeah,
Yeah.
yeah,
So you
Krishna.
can correlate.
Studied.
Correct. You can correlate these concepts there, saying that we will have something done on an image, we'll shrink it, and then later on we'll pass it, we will again recreate it and pass it to our network. Now, why do we do that? Very simple thing. I've reduced my dimension, I've retained the data. All right. Now, what are these encode and decode? Very simple. It could be your fully connected neural network. Design a network whose outputs are little lesser as compared to your original input. How many ever layers you want it? How will you design these layers? Depending on this. So first of all, you have to decide the decoding size, how much you want to decode up to. Okay, and then finally you design inverse neural networks. Keep training them unless and until we are satisfied that both of them are almost similar. This is called auto encoding. It's not a very popular way to do it, because definitely in future, if I have 7, this image will not be 1 megapixel. Okay, I want to take HD images and shrink it. And if I take an HD image shrink like this, definitely I'm going to lose some data out of it. Everybody agrees to that. We cannot completely recreate this, no matter how good our network is here. Okay, so this is your neural network, simple one. This is also a neural network. You train the weights back and forth till they both sync up. All right, so this is an auto encoder. I'll show you one implementation down the line. Yeah, so what I was asking here. Yeah, so so in other cases, what Google has done is they have done max pooling. So also you can think about max pooling as a dimensionality reduction. Yeah. So let us say if you have an image, say my favorite number 32 cross 32. Okay. Now, if I want to if I want to replicate this image into 16 cross 16, what I'm going to do? I'm going to max pool by 2. 32 by 2 is 16. Very simple. You can do this, or you can do the one which I showed you. Anything is okay. Okay. So this is your Google Net. We will take this particular network at the end of the module so that you are very comfortable and you don't get confused, because by looking at it itself, it's pathetic, it's horrible. And to understand this, I'm not sure even if this is open source. I'm still seeing to it if we can download it. Else what I'll do is we'll do a very good in-depth theoretical review onto this. What is it and how they got hold on to this. Okay, and what is the application of Google Net. All right, now if you compare the most popular ready-made networks available, you will find them over here. If you look at this, the most stable one is VGG. So down the line, I think almost all of my implementations, you will find VGG itself. It's very simple to work with VGG. Okay, and look at the accuracy also. VGG is not very great. It covers around 65 to 75, but yes, from the parameters point of view, it is showing one of the highest parameters available. More the parameters, better will be your learning. Okay, LXNet and Google Net lies somewhere here. ResNet is somewhere here. ResNet 152. Okay, so 152 in the sense you are having more parameters. That's it. More number of deep layers as compared to 18, 34, and 152. ResNet 50, ResNet 101. So different versions are there. Okay, so this is how you can visualize this particular graph. So I will say, if you guys have decided to transition your career onto computer vision, then you need to know some of the most popular ones like VGGs. I will say LXNet, Base 1, and say ResNet 152. So if you know these 3 algorithms, you can say, yes, I know computer vision. Yeah, because they are the top performers, if you see, except LXNet. LXNet is the one very basic one, but these 2 are kind of top performers here. And also try to correlate them with the number of features available. Okay, good. All right. Now coming to the concept of transferred learning. So too much of theory. We'll come down to this very simple diagram. I have got a source task, let us say some task, generic one. I'm putting and I'm running a lot of hardware onto this, and I'm putting it to my knowledge. Now what do I do is I've got my target task. Yeah, let us say our real-time application, which I want to use it on.
I get my data, I import your learnings onto my learning system, and I classify my stuff. That's it. So you don't have no more. We have to do the classical, traditional machine learning way of doing it. Train your model and then use your model. No need to do that. Use ready-made learnings to move on. So this is your transfer learning. And if you look at the learning curve also, to be very frank, this is a better one, obviously. And majority of my implementations that I do, I take a ready-made network itself. I don't take a pain of doing CNNs. Now you may ask me, okay, fine, then why are we learning it? You will understand CNNs, the use of it after week number 4, where we enter RCNN, fast RCNN, YOLO, SSD, all the complex algorithms that we enter. No? At that time, again, we have to use CNNs. We have to use some part of it. So the concept of building CNN is okay. Great.
This brings us to the end of this course. So thank you very much and have a great learning ahead.
I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.